in Germany, Canada as postdoc. Then I joined here, and I did my physics bachelor. Before joining to Columbia University, I was in IIT. So we will have a nice. Where are you from, and where are you joining from? Okay, who will go next? Hello. So yeah. Okay. So you can all turn on the video. At least I should know first day with whom I am talking to. Is it possible to turn on the video, or if you are not ready, then we can turn on the video next class? Is that okay? Which one? Because I need to know, no, at least the face who are my student, like that, you know. So that's very important, and you should sit like, this cosmology is not so easy. The concept. So is it possible to turn on the video, or you generally don't do it? Hello? And it's okay, but at least you can turn on and then switch it off. Not all the time. Okay, we need to, at least we can introduce, no, this much. Yeah. Okay. Hi, Shruti. Okay, very nice to see you. Okay, next, Ravi is my PhD student. Ravi, you can turn on the video, and he will be helping you if needed little bit later. He is a very good student in cosmology. Yeah, Ravi, you can introduce yourself. Yeah, he is coming from
Hello,
IIA. Yeah.
hello all. So I'm a PhD second year student at IIA. I'm working with sir in theoretical cosmology.
Next, who would like to go? Yeah.
Hello, sir. My name is Gauri Shankar. I'm an integrated MSc student at Pondicherry, and I'm currently joining from Kerala.
Kerala. Okay. The university is still working online, no? No,
Yes, sir. Yes, sir.
students are there inside.
Only
All
PhD students.
okay. Okay. Only PhD students are in campus. Okay. So next, who will introduce?
Sir, good morning, sir. I'm
Yeah,
Arpita.
Arpita.
I'm from Kerala. I'm an integrated MSc student, Pondicherry.
Oh. You are also at home now. Yeah. Yeah.
Yes, sir.
Okay. Okay. Great. Next, Priyanka. Can you hear me? Yeah. Okay, Avinash. Yeah, Avinash, you can go ahead. Yeah.
Hi, sir. So I'm Avinash. I did my UG from Loyola College, Chennai. I'm a regular student at Pondicherry University. Right now, I'm in
Okay. Now you are in Chennai or
Kerala.
Pondicherry. Kerala. Okay. Good. Okay. Next, Priyanka. I can't hear you. You have to unmute, Priyanka. We can't hear you.
Hello, sir. I am Priyanka from Pondicherry, doing MSc in Pondicherry University.
Okay, you are from Pondicherry only.
Yes, sir.
Oh, okay. That's good. Okay, good. Jahang? Yeah.
Hello, sir. I'm Jahank. I'm a final year MSc student in Pondicherry University, and I'm basically from Kerala.
Okay, very nice. Great. So, anybody missing, or all of you are here? 1, 2, 3, 4, 5, 6. There's 7 students, no? One person missing. Who? Okay. You can message that we are starting. So, let her join fast. Okay? Okay, great. So, today's lecture will have mainly little bit on a note sharing, a note, because today is the first introduction of cosmology. From next onward, I will do the pen and paper. Pen and paper means I'll work on the pad so that you will see that as if it is like a whiteboard. Okay. Has anybody done, any of the teacher done that board work with you?
Yes, sir.
Yeah. Rajguru sir has done it, no? Like that?
Uh,
Or who?
Not in Astro. I mean, now physics courses. So,
Oh, physics, not in this astrophysics course, no? Okay.
yes, sir.
It is much better if I do like a board work, no? Then you will feel like it is in the classroom. Isn't it true? Yes?
Yes, sir.
Yes, sir.
Yeah. Okay, good. ठीक है. So now today as the first day I will not do the board work. So now I am also switching off my video time to time, but I'll turn my video on. And if you have asked any question or anything, please turn the video on and it will be better. At least every class we should turn the video on at least once or twice to say hi, because then it feels. Otherwise, in Zoom, you never know with whom you are talking, whether you are at all there or not. Okay, it's good to have little bit of discipline. What do you say? Yes, then your attentiveness will also remain. Yeah. Yes.
Yes, sir.
Yes, because otherwise online lectures are not so easy. It's very stressful if your attention goes away. Okay, very nice. So these lectures is cosmology. I'll take 10 lectures and I'll cover basically the history of our universe. Okay. So what is cosmology according to you? Can anybody speak this time before we start? What is cosmology according to you? Cosmology का definition क्या है? It can be right, wrong, whatever you have idea in mind. What is cosmology? Can you guys go ahead? Who will go first? Be free, because if you want to learn, yeah, you can. You will be able to ask stupid questions. You will be able. You should not be scared to ask stupid questions. Okay, that's the problem. Then you never learn unless you ask stupid question. Okay. So yeah, who will go first? What is cosmology according to you? Yes.
So I think cosmology is the study of beginning, evolution, and like in the end death of the universe.
Beginning and the sustenance, and at the end what will happen. So basically it's like a life story of the universe. Okay. Yes. So like all of us have life story. We were born, then we did this like that, and we came. Okay. So next, anybody else? What is your definition of cosmology? Who will go next? One thing is missing in the definition. What Avinash is doing, it is not just the time. He talked about time, beginning of the time to the end of time, but there is space also. Yeah. So how far we go? What is the length scale we go in cosmology? Who will go next? Any idea? Who will go next? You can say, what is cosmology according to you? You can hear me, no?
Yes, sir. Study of entire cosmos as whole.
Study of entire cosmos. Who is this speaking?
Gauri Shankar, sir.
Okay. Yeah. Study of entire cosmos. How much distance? Cosmos. Whether our universe is finite or infinite. Who can give the answer? You can either chat box also you can use. How many of you think that universe is finite, and how many of you think universe is infinite? Can you give your answer? Everybody should participate. Okay. Let me see what is your idea about the universe. Then only we can study. Write quickly. Okay. Finite or infinite? Okay, Gauri Shankar is saying universe is finite. You don't give me direct message, give message in public so that everybody can see your message. Okay, answer. It is like a class answer. Okay. Next, everybody should write whether universe is finite or infinite, or you can say. Oh, only direct message is possible. Let me go and. Anybody knows where to change that to enable the. Ravi, do you know how to enable the message to all the people? Maybe I have to open the chat box, then only I can do that. Yeah. Okay. Now I think, can you try, all of you, that two messages, whether universe is finite or infinite, or both? Gauri Shankar has messaged me, it's finite, but now you can put it in the chat box. Let us do quickly, okay? Other people, please write. Yes, observable universe is finite, but beyond observation there is something. Okay, Avinash. Uh, okay, we are seeing only the finite space. We don't know. Okay, anything? Anybody else who goes next? Everybody should say something. Priyanka, Arpita, Hangi.
Sir,
Yeah,
the thing is always expanding, right? That's what we know as of now.
is expanding.
Yeah,
Yeah,
so
that we know. Uh,
so
so
there is uh, there should I don't know, but as it is expanding, there should be something to it. It is filling up to. That's what my. So I don't know whether to say it is
okay,
finite or infinite, but still there is. We need much more clarity to say correctly what exactly is happening.
okay, good. So, Jahang's point is, if it is expanding, we know, then has to be expanding into something. So that means there has to be a boundary.
Yeah,
So
correct.
mostly it is finite, but we don't know.
Yeah.
Okay, and okay, good. Priyanka says that it's infinite. She has no doubt. She says it is infinite, must be infinite, and Shivardhini is agnostic. So like it may be finite, may be infinite. Okay. So Shivardhani, we have all introduced ourselves before you join. You can also turn on the video if possible. So everybody turn on the video. Introduce that. Where are you from? ऐसा करके. Or you can just speak. Can you hear us,
Okay. Yes,
Shivardhini?
sir. I'm Srivardhini.
Yeah.
I'm from Chennai. So, yeah, final
Chennai.
year master's in Pondicherry University.
Oh, good. So, if possible, turn on the video once. At least we know whom I am speaking to. Otherwise, next class you can turn on the video because
Yeah, I will do it in next class.
okay, no problem. Because we have all agreed that we will time to time turn on the video in every class so that we feel we are like a classroom and we'll move together. Okay, so here is the answer to the question. Two things here. I'll go into the detail. First of all, our observable universe is finite. Why? Because we know for sure that at least the time we experience in universe is finite. Space we don't know. So there is a age of the universe which we have all measured, and that age of the universe is this one. So can you see the screen?
Yes, sir.
Yeah. So starting from the beginning, t equals to 0, it might not be totally like the resolution might be not so good. But today we are around 14,000 million years. The human we are sitting here. So the actual age of the universe is around 13.7 billion years here at the end. So where the human is sitting and trying to understand the universe. So do you know that? You know that the universe age is 13.7 billion years and it has been measured by uh, cosmic microwave background radiation. Did you? How many of you knew this before? You can write yes or no first time. Universe is 13. I am writing it. 0.7 billion year. Billion year means you know that 1,000 million is 1 billion year. So in terms of crore, I think it is approximately like this 1,000 crore years. So now, can you tell me that in theory, what is the largest distance we can experience naively? Because to see something, the light has to reach to us. Yes or no? You can sometimes give this thumbs up. This is yes. Okay. Yes. So, what is the furthest distance we can see, given the finite age of the universe? What will be the approximate answer? Can you tell me? Who can write down the answer? It's very easy question. What is the distance, furthest distance we can theoretically, or even with the highest technology, we can see that much. Beyond that, it is not possible today. Okay, why 46 billion light years? Because the age of the universe is 13.7. Yes, Avinash?
But like there is the acceleration part also in the expansion. So
Okay, so that is the more detailed part. We'll go into that. But naively, if you don't know anything about the universe, if you just know that the light, the oldest light you can see is 13.7 billion year old. Yes. So the oldest distance, the farthest distance you can see is 13.7 light billion light year away. Is it clear to everybody? Naively. What Avinash says, I'll go into the detail, but at least that is true, because if you are seeing a star, so for example, I'll go into the screen sharing mode again. See this one. Go into the lower part. That there is a supernova which we 1987 A supernova. Okay, we measured it in 1987. Okay, by powerful telescope, supernova burst. So its age is 170,000 years. That means it is 170,000 light year away from us. Okay. So this exploded. Whereas before that, the dinosaurs which got extinct from our planet, because of that Homo sapien can only come, it is 65 million years old. So the supernova we are seeing is little bit after the dinosaurs, okay? Not little bit, quite. But before the supernova exploded 170,000 years back, there is dinosaur, and before that the mammals has evolved in the planet, and the earth, earliest life in the earth is 3.8 billion years old. And I am going into the lower slide to the left direction, and the birth of sun is around 5 billion years old. So you see that out of 14 billion years, first 8 billion years there was almost our habitable stars are formed much later, 8 billion years later. So universe waited quite a bit for the first star to form, and then we appear very late in the universe. So you can see before the supernova explosion we happened there, we appear Homo sapiens around 600,000 years back. So compared to the age of the universe, we are a very recent phenomena in the universe, very late. Okay. So now let's go to the above slide. Now let us go in the beginning of the universe. Now we are going to the beginning, second to the million years. Beach may in the middle there are 8 billion years we are skipping today. Okay, because that time what happens in the 8 billion year is almost like dark ages of the universe. The stars was not born, universe waited, because the gravity was basically clumping the hydrogen and helium gas and were trying to form the stars and galaxies. But it started efficiently forming around 5 billion years. There are billions of suns appear 5 billion years or 4 billion years or 6 billion years that time. So first 7 billion years were like a preparation. Okay, like you prepare for so many years to do a PhD and ultimately get PhD 5 years later. Okay, So like that, universe was also preparing for human to come. And let us go into the beginning. Till now, we have seen the earliest epoch of the universe is almost 100,000 years back. In between these 2 points, you can see above, there is a radiation era and there is a dark matter domination. In beach may there is a in between there is a thing called cosmic microwave background. How many of you heard about cosmic microwave background? And that is the earliest we have observed till now. Before that, all these things are theoretical model that at 3 seconds the basic elements form like hydrogen and helium. At 10 to the power minus 6 second, actually universe shaped and the quarks forms the nucleus. Okay, and 10 to the power minus 35 seconds up to that our physical laws work before and if you go beyond that all equations breaks down. So big bang, that point of t equals to 0, nobody has yet able to describe what is the physics there because it is called a singularity. Singularity means if you write down the equations, it also breaks down. It gives 1 over 0, 1 over 0. So up to 10 to the power minus 35 second, we are pretty good. So it's also dramatic that 10 to the power minus 35 seconds, we have mathematical equations and there are all these hotspot, no, universe shaped, 10 to the minus 6 seconds, quark formed. There has been paper, there has been publications on that, there has been simulation, and it all matched theoretically, but direct observation is still 0.3 million years. That means around 1000, or I would say 0.3 times 1000 100,000 years. So this is the thing. The earliest light we have observed is from 0.3 million year old. So it is from the beginning, 0.3 million years. From now, if you go back, it is almost like billion years, 14 billion years. No, so this is the idea. How many of you heard about cosmic microwave background? Can you write yes or no? Because time to time I'll ask you this question and you should type so that I know that you are all there. Okay. How many of you have heard cosmic microwave background? Yes. Yes. And if you have not heard, you can say no. Okay. Yes. So all of you have heard yes. Okay. So now let me tell you this thing. Can you see this my white thing? I will not do boardwork next to class like this. I'll have a pad, so I'll write it down. It will show up in your PDF screen in the computer. But today I don't have, because I have ordered it from Amazon. It will come tomorrow. So now you can see this.
Yes, sir.
Yes.
Yes,
The
sir.
white thing, and can you see the write up what I have written
Yes, sir. Basic cosmology.
or not?
Yes, sir. You can see it.
Okay, then it's good. Okay. So now what happens, as I was showing, that around 3 seconds of the universe, 3 second old universe, hydrogen and helium formed. Okay, it is called Big Bang nucleosynthesis. We will come to that on detail in the class. But today I am giving you an overview. 3 seconds. So just after Big Bang, 3 seconds, the hydrogen and helium form. But to form hydrogen and helium, you need to form nucleus, and that happens around before 10 to the power minus 6 second. 6 second. It is called the nucleus form. It's called QCD, quantum chromodynamics. You don't need to know. Nucleus form at 10 to the power minus 6. But nucleus alone is not universe. This thing, it is hydrogen and helium has to form, so atom form. But even if they form, there were a lot of photons. They were very energetic photons in the universe, filled with photons. So if an hydrogen atom is there, and if a photon collide with the hydrogen atom, what will happen with the energetic photon? Who will tell? Give me the answer. This is class 12 modern physics question. Hydrogen atom were there formed, but there were plenty of photons. So what will happen? What will happen to the medium? Billions of photons. It will ionize. Avinash, good. Ionize. Yes, yes. So it will be like H plus and E minus. Okay. Other people write something, yes or no? Agreed? If you say yes, then you should write yes. Yes. Ionize, yes. So now, yes. Now, as you know, this is the plasma. Because there was no way an atom, neutral atom can form, because every time it will form, the photon will come and it will kick the electron out of the orbit. And that is called ionization. Because photon has huge energy. They are very hot universe. A wavelength, like the photons are very hot because it's the temperature of the universe is very high in the beginning. So now, how atom formed? Then if it was always hot, atom could never form. But universe is cooling down. Yes or no? Why universe is cooling down? Can anybody give me the answer? Let me see. Right, wrong, doesn't matter. Just write down your answer, because online manner, it's very hard to communicate, because in classroom I can talk, I can directly ask. So here, so other people, please write. You can give the public answer, okay? Not the individual answer, so that everybody know your answer, okay? Not to me. Priyanka said it is expanding. Other people, please write. What is your answer? Because universe is expanding and density is decreasing with a question mark, expanding. Because it is expanding. Very nice. It is like a thermodynamic gas, a balloon. So if you expand the volume more and more, the balloon, the gas cool down. Okay? Because it is like a thermodynamic simple law. We'll do it in the cosmology. When we do the thermal history, we'll see exact thermodynamics law apply on the universe. Okay? And it will cool down. And it will cool down as how the temperature should go, as we will tell you later. There is something called scale factor. Today only we will do scale factor of the universe, which I'm not explaining you right now. It is called scale factor. Today at the end I will explain you very soon. Scale factor. So scale factor is basically a factor which is stretching the universe in every direction. Because we all know that Hubble discovered that the universe is expanding. So how many of you knew the scale factor term before? Can you write it down? Scale factor. Yes or no? I need to know. Or you can give the thumbs up quickly also. You knew or no? No. Okay, Abhinav said I didn't know scale factor. Very nice. Other people? No. Jahan says no. Very nice. Okay. Shruti? No, sir. Okay, almost all of you did not know what is scale factor. Very nice. So, scale factor. So, you know that the universe is expanding. Now, universe is expanding in all directions, all three directions, or in one direction?
In all directions.
Which is the answer? All direction. Very nice. All direction, we know that. It's a universe doesn't prefer one direction. We will come to that very soon. So, if it is direct, and it is expanding in equal rate in all directions, more and y-axis, then you will have a deformed universe. Yes? Yes? If you stretch different axes in different factor, then things will deform. A sun will deform, galaxy will deform, cluster will deform, because they are stretching in different, but it is going in all direction equally, so that it is keeping its shape, but it is expanding, universe is expanding. So now, this is the story of the expansion of the universe. Now slowly I am moving into the geometry, slowly mathematics. So suppose I have a coordinate system. Okay. So now, if I have 2 points, P1 and P2, what is the distance between 2 points? I call it ds square, distance square. What is that? Distance square in Euclidean geometry. You have done it, no? Cartesian coordinate. What is the distance? You can say it also.
Root of dx1 square plus dx2 dy1 square plus dz1 square.
Yes. Everybody. So I am doing distance square. So it will be like dx square plus dy square plus dz square. Clear? I am just drawing 2 dimension, but it is 3 dimension. Is it clear? You all know it. Dx is the x1 minus x2 square plus y1 minus y2 square plus z1 minus z2.
Yes, sir.
Yes? Time to time give this thumbs up so that I know that you are listening. Okay? Now, if universe is expanding, then the distance between P1 and P2, this formula works or not? Yes or no? Okay, let me ask you a question. Suppose universe is expanding. Today all of us measure this distance between 2 points, and we find that this distance is dx square, ds square, and we find a value. So today we measured and we find a value, I call it ds0 square, because today is the naught, ds naught square. This is just a suffix. Now suppose 1 million years later, somebody comes and again look into this 2 point. Now how the 2 point, so this point is x1, y1, z1, and p2 is x2, y2, z2. This is like the coordinate. Okay? And you can think of it like a balloon. Okay. So now if 1 million years later somebody comes, what he will see? He will see that the distance between the grid has become bigger. Yes, because every direction universe has stretched. Yes or no? You can give me a thumbs up. Because it has become bigger. That is what he will see. Suppose imagine a balloon and balloon is expanding. It's like, array, distance between grid is becoming bigger and bigger. But does the point coordinate change? P1 and P2, the write up on that? Yes or no? Can you write it down? He will still see that this P2 is x2, y2, z2, and P1 is x1, y1, z1. Because the points are points. How you label them? Yes? The coordinates every point, but the unit distance between each grid has changed. Yes or no? Yes. So if you use this definition of ds square, will that be a correct definition of the true distance between P1 and P2 for an expanding universe or expanding balloon? Who can give the answer? Yes or no? Because suppose there is a computer, it comes after because it is coded, it just looked into the coordinate and then do x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. Then it will give the same distance, but actual physical distance between P1 and P2, is it same or it has become bigger? You
It
can
has
say
changed,
it.
sir.
Huh?
It has become bigger, sir.
Bigger because it has, but the coordinates are the same, isn't it? Because you created the grid. Yes?
Yes, sir.
So then what to do? How to write down the distance? Any suggestion?
There should be some
True distance?
coefficients.
There should be some factor in front of this. And that factor, what we are going to do, we say like, okay, now this Cartesian coordinates is only true if space does not expand. Yes, Avinash multiplies same factor. So we will do ds square is equal to at square times dx square plus, I will show you dx square plus dz square. I'm multiplying with a factor AT square. And this AT is a monotonically increasing function of time. So if you measure after 1 billion year, it will become bigger. It will become bigger. And if you measure before, earlier time, it was smaller. So depending on when you measure the distance between 2 points, you get different distance. Is that right? Is that make sense now? Yes, you can give a thumbs up. It's very simple.
Yes, sir.
AT. And why I have not make A as a function of X or position? Why? Only I have given it T. Who can give the answer? Because, who can give the answer? Okay, let me see. Anybody has answer? I have only made it function of time. Why I have not made it function of coordinate? If I make it function of coordinate, then what will happen? Different point in space will expand in different,
different distance.
and then it will be deformed and will not end up in an homogeneous and isotropic universe. Okay, I'll come to that. So that's why it's only function of time. This is called scale factor. So this scale factor A T is 0 in the Big Bang, time of Big Bang. That means if you multiply it 0, then everything becomes 0. That means all distance is 0. That means there was no space. Is it clear? Because Big Bang is, suppose everything is now expanding. So if you take the movie back, take the reel back, then everything was coming closer, 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 closer from all direction. And then at one point it will all collapse in one point. So that point there is no space. That's why AT is 0 at the Big Bang. Yes? Agreed? Yes? Yes? And AT will be much bigger than Big Bang till now. Okay? So we cannot take 0 here, because if we take 0, then we cannot do any mathematics. That's why I have shown you in the slide that I have taken 10 to the power minus 36 second earliest. That is where our theory, we know quantum gravity works. Okay. Before that, if you write down the equation, everything will collapse. Okay. You get infinity 1 by 0. In two cases in cosmology, we get singularity. One is in the Big Bang. Anybody know where else we get singularity?
Black holes.
At the center of black hole. There also the space-time completely cracks. Means like we cannot define space-time. So that's why if you understand the beginning of if you understand the black hole center, it will be very similar to understand the beginning of the universe. That's why people have that idea, that many people have speculation that maybe black hole, if you hit the singularity, it is the similar singularity of Big Bang, and you go beyond the space-time and you end up somewhere which you don't know. That's the Interstellar movie. Okay, up to the falling of black hole, it was good. Interstellar movie. How many of you have watched Interstellar movie? Anybody has watched here? Who has watched Interstellar movie? If you have not, okay, Shruti has watched. Anybody else? Yes. Okay. So if you have not, you should watch it, because after understanding GR little bit, though in this course we will touch GR, but we cannot complete, of course. GR itself needs a full-fledged 2-semester course, but we will do little bit of GR, okay? But mainly cosmology. So you will see there that the person falls into black hole and he enters into another dimension called hidden dimension, okay? And it is here only. So that is the speculation in string theory or any other places, that if you cross our physical space-time, it's not that you go somewhere else. You remain here, but you don't have access to this space-time. You enter in a parallel universe. Okay, so it is like radio frequency. If you tune in to 93.5, then you will hear all Arijit Singh or all Hindi song. And if you go to 90.1, you will sing Kannada song. But it's all frequencies are here. Okay, so like that, all dimensions are here, but whatever dimension you are, that's where you have your experience of reality. And in string theory, out of 10 dimension of space-time, why I'm talking string theory? Because that's the only theory which can match the gravity and quantum mechanics at the time of Big Bang or black hole. Okay? How many of you heard the word string theory? Yes? Before? Because you know that gravity and quantum mechanics, when you want to merge them, it gives zeros. You don't need to know all this. This is not part of the syllabus. I'm just telling you. So, black hole singularity and Big Bang singularity are very similar. I know you don't understand them. So now this part is clear. Now coming back to this, AT is 0 singular at the time of Big Bang. And now we generally work with AT starting for 10 to the power minus 30 or 10 to the power minus 40, at least 10 to the power minus 40. From that time onwards, we pretty much know what has happened in the universe, as I was telling you. Okay, showing you that quark became nucleus. These are happened very early. And before that also something happens. You have heard about Higgs Boson. How many of you heard about Higgs Boson? God particle? Yes? How many? Yes. You can give the thumbs up. So basically that happens. The Higgs Boson gives mass to all the particles. Just after Big Bang, everything was moving in the speed of light. Everything. So if everything moves speed of light, then their mass is how much? Can you tell me? If speed and mass is related. Jahang is saying exactly. Whatever moves in the speed of light, its rest mass is 0. So everything was moving in the speed of light. So every particle was 0 mass. So you cannot differentiate between heavy and light. That definition did not exist. That quark is heavy, electron is light, neutrino is light, or some other particles are very heavy. ऐसा कुछ नहीं था because everything was moving in the speed of light. Then Higgs came, Higgs field. It was there, means then it does something. I will not go into that. It's particle physics. I teach that course in IISc, particle physics course, but it is not here. But I tell you, Higgs slow down the particle. And it slows down differently with different particles. So Higgs is like a so you can think that Higgs did. So suppose this is like a pond where all the feces, different feces are there. All feces are different particles, and they are all moving in the speed of light. Then what happens? Higgs does something, and it makes the medium interact with the fish in a different magnitude. And the moment medium starts interacting, it gives a friction, and different fish slow down in different rate. And different fishes are different particles. So depending on its interaction strength, the slowing down happens. So Higgs slowed down the quarks very heavily. That's why quarks became very massive. Higgs slowed down the electron with less intensity. That's why electron remained. But Higgs did not interact with photon. That's why photon remained. Who can give the answer even today? Yeah, what is the answer? Massless. That's the whole history. This happens around even much earlier, around 10 to the power minus 46. I'll give you the number. Can somebody find out this number? I am forgetting it. I think 10 to the power minus 46 when A was 10 to the minus 46 or 50, the scale factor. Okay? You can find out from all these things. So find out the value of scale factor when Higgs gives mass to particle. Find out the value of scale factor when quark become inside the nucleus. Okay? And find out the value of scale factor when hydrogen and helium form. These 3 things is your homework. Okay? Ravi will give you the homework in write-up. Yes, Ravi, can you give the homework in 3-4 lines? Okay? Yeah. That find out these epochs. You can just do Google search to get an idea. And then, what are the next epoch? That I am going to tell you soon is the cosmic microwave background. But first 3 seconds of the universe was very busy. Okay? Universe did its maximum work in the first 3 seconds. Okay? And all the force emerged from gravity, electroweak force, and the what is that called, strong force of nucleus, weak interaction force. These are the three forces, and gravity, four forces. In the beginning there was only gravity, then other three forces emerged. That also happens. It is called electroweak symmetry breaking. It also happens in the 10 to the power minus 40, 50. So all happens in much before the nanosecond. Nanosecond is 10 to the power minus second. So universe just creates big space and time. Within nanoseconds, most of the thing done, and then within first 1, 2, 3 seconds, hydrogen and helium formed, and then universe says that all the particles has been created, all the force has been created, basic stratum of photon, all the particles got mass, and helium, hydrogen with ionized, of course. It, as you say, it cannot be neutral, but at least their medium is created, and that plasma, hot plasma, is called hot Big Bang. Because when people say what is Big Bang, we don't mean that there is an explosion. We never know that whether there is an explosion or not, because we cannot go into a to the power a equals to 0. It breaks down. So all we know that at 10 to the power minus 40 seconds onwards, something started happening. Higgs came in. Then all we know that universe was in a hot plasma at 2 to 3 seconds of the universe. The 3 second we see it indirectly. It's called Big Bang nucleosynthesis. We have not directly observed, but we have directly observed the CMB photon, which is after 3 seconds there is a gap of, and we observed it 0.3 million years. So 0.3 into 10 to the power 6 years. That is the first observation we got, and it got Nobel Prize. But that also pretty early. If universe is 14 billion years old, then 0.3 million years is like nothing. It is like if a human being lives 100 years, and first day is called the baby, no? So 0.3 million years is like the baby compared to the 14 billion years. Okay, so that's why the cosmic microwave universe, what we see today, is called baby universe. 0.3 million years is like the first day of the life cycle of the universe, because universe is pretty big and pretty old. Is it clear? If you take the ratio of 0.3 million years when you see the first hydrogen atom form compared to the whole age of 14 billion years, is the same ratio a baby is born one day compared to the 100 years. Okay, or even less. Okay? So that's why we call it a baby universe picture. But baby universe is already 0.3 million years old. Okay? But still, that time what we see from cosmic microwave background is actually it's like a plasma state with little fluctuations, and neutral hydrogens are just getting formed. Clear? Yes? Yes, so this is the brief history of time we are giving. So find out the scale factor value when it was releasing hydrogen, for electromagnetic radiation of cosmic microwave background. That is the next step I am telling today, and I'll take another 15 minutes, then we'll be done today. So now I'll go back to the thing, dA square again. So dA square is AT square sum over dxi square. I is 1, 2, 3. Okay, this is the Cartesian coordinate in expanding universe. But here we have not taken time as a dimension. But you know that time also enters this distance between space-time, because in Einstein's special relativity, the distance is not between space, distance is between space and time. Agreed? Yes or no? Give me a thumbs up. Yes, yes. So what is the distance? How do you write the distance in Einstein's special relativity? When you first consider time as a dimension, what is the distance? Who can tell me? Forget about space-time now, expanding space-time, forget about it, the special relativity. How do you write down the distance? Who can tell?
T square dt
Or
square
time?
dx square minus d square minus dz square.
So it's basically c square dt square plus something like that. Agreed? Have you seen this? How many of you have seen this before? This is a metric. If you have not seen, you should read a little bit of special relativity metric. It will be in the BSc physics course. Definitely you should know this, because some university, they don't go into the metric form of special relativity. How many of you have not seen this metric? Anybody? No? Write down no, that if you have not seen. That this is the true distance. Only one person said, I have seen this metric. No. All other people have said, yes, you just give me a thumbs up because I cannot read all the things. Yes, you have seen the metric, thumbs up. Okay, then it's good. So now, this metric has a different sign, minus in front of light. That's why the time is not exactly like space. It comes with a negative sign. Some people write here plus, then you have to put space as negative. It's just a convention. Or some people write here minus c square dt square plus dxi square. Some people write plus c square dt square minus dx square. It doesn't matter. Okay? Different convention. This space-time has a name. Do you know what is the name of this space-time of special relativity?
Minkowski space-time.
Minkowski space or flat space. Minkowski space or flat space-time. Flat space-time means, I will come to that in third lecture or fourth lecture, that there is something called curvature of the space-time. That curvature is related to the gravity. That's the discovery of Einstein, called general theory of relativity. You have heard about this term, general theory of relativity? Yes, you can give the thumbs up. Yes, if you know. And there is something called curvature of the space-time. And why intuitively curvature is related to gravity? Curvature means how space-time is curved. Okay? So this is what I am telling you now, because as I am introducing curvature today, this has no curvature. This I will not go into the full details of curvature because that will take 5-6 classes. But I will give you a note where you can derive or get into the idea of curvature. Given a metric like this distance, if somebody gives you, you can calculate in the Mathematica code, or there are software codes. You just give the metric, they will calculate the curvature of space-time. So why distance is related to curvature? Because you know that. Suppose this is Earth's surface. If Earth's surface is flat, you can go from here to here penetrating. But if Earth's surface is like this, then you don't have access to go like this, through this. You can do, but aeroplane cannot go like that, okay? So they have to, if you keep walking, then you feel you are walking on the straight line, but actually you are walking on the curve, and you will travel much more distance. So your shortest distance is actually this. But if the space is flat, then your shortest distance will be inside this. Is it clear? So depending on geometry, the shortest distance changes. How many of you got this idea? Clear? Yes? Yes. So that's why, if you know what is the distance, that's why I am writing the distance intuitively, then you know what is the geometry. You know the curvature. Okay? So with Minkowski metric distance, if you find the curvature, there is no curved in the space. Now, you cannot visualize, here you can visualize because it's a 2-dimension. But 3-dimension and time curving into each other, you cannot visualize. Because first of all, the time itself is a dimension only Einstein could visualize. Nobody else, okay? Still, I am studying for 15 years of general relativity. I still cannot visualize how time can be dimension. But mathematically, I know. So, you cannot visualize how space is carving into time, okay? But one thing is sure, if time is also curving in the space, then as like I said you, the distance between space is changing if you have access to a direct line, or if you don't have access to the direct line, then you have to curve, it will be much bigger. In the same way, the time interval will also change depending on the geometry. And that is the reason the delta t, like here delta x distance, changes depending on the curved surface or like a direct axis. Like that, the distance between two time, say between two clock tick. It's 1 second here, but if you go in the gravity, the same clock. So 1 hour of gravity, high gravity zone in black hole will be like 100 years of human life. Just like space takes different distance, you are feeling that you are walking in the straight line, but you are actually covering, going from Russia, then Europe, and then ultimately you are reaching, say, Spain. Okay? But if someone has access directly to the Earth's surface inside, it will reach much faster. Same way, the time you feel that it is just 1 second for you, but it might be 100 years for somebody else. That is reality. So you can see the perception of time is very relative. Okay? Not that the psychological time. Psychological time is also very relative. Suppose you are quarantined in your hostel room, time does not run. Okay, oh my God, how long I will be quarantined? My next door has got corona. I am a direct contact. But if you are walking, talking, people, here se time pass ho jata hai, how time pass you even don't know. Agreed? Yes, that is psychological time. I am not talking about that. The actual measurement of time, biological time, heartbeat, the gap between all these things change from here to black hole. That's why it's a reality that if your twin goes to black hole, spend 1 hour of his clock and come back to Earth, he will see that he has aged by 1 hour more. But he will see his twin, maybe you, has become 80 years old. You have heard about it, twins paradox? Yes? How many of you have heard about it? In twins paradox, it is related to velocity, because in relativity is the velocity which does time dilation. But here, in general relativity, it is the curvature of space-time can also make the time curve. Okay, because as space is taking longer, and space and time are very similar. If time also curve, then in the time-space, you have different way. In black hole, you have a shortest way between 2 points. But in Earth, you have a longest way. That means the same 1 second in black hole looks like 50 years in Earth, because the curvature happens differently. Okay. Is it getting intuitively clear that like space can be different distance happens as you can travel, like that in time also if it curves, you cannot imagine it, but it's making sense. Yes? Yes? Okay, very nice. So now, if we go from here, and if you want to include this expansion of universe 80, then actual metric will be c square dt square, then this 80 square time dx square plus dy square plus dy square plus dz square. Clear? Because special relativity does not include the expansion of the space-time. So the true metric for the universe is now not the Minkowski space-time. Minkowski is the flat. Now we have this new metric which is minus c square dt square plus a square t dxi square. Now you can write down this dxi as in spherical polar coordinate. Then it will be dr square plus r square d theta square plus r square d theta square sine square d phi square. Sorry, r square d phi square plus times sine square d theta square. Clear? Is it clear? Yes or no? Yes or no? So this is the metric of the universe. This is called FRW metric. Friedman-Robertson-Walker metric of the universe. We will start from next class from here, and we will see that if you know this metric, that universe, that means it is also taking time into a dimension, which we should. It is also taking care of the universe is expanding by a 80 square factor. Okay, and we will be amazed to see in the next class that from this, and knowing that light moves in the speed of light, we can find out the concept of redshift. Redshift means if some star is far away and the light is coming to us, we can exactly tell if the emitted wavelength is lambda naught, how much wavelength we will see today. It will be stretched because of the expansion of the universe. And depending on the further away it is, it will be further stretched. Stretched means it will be redshifted. Yes? Okay. Very nice. So this much is okay for today? Yes? Yes. So I'll send you a note, little bit, and you read Colvan Turner and all this thing, and you will see that this is the first idea of the course.